with a simple device.
Great. Now I want to get into a little bit about the pump itself and how that works. I want to remind folks that we can start taking calls at any time. Just dial *1, and otherwise I'll just run through my questions and we'll bring it to a close. If you could go into the pump itself, and I know there's not much we can see, but again, people can go to the website and see it broken out schematically, both as a photographs and in the paper as a diagram. Talk about how this pump works, because this is a new device. This is something that, before this paper is presented, this has not existed before, and it uses a Synjet technology, which Synjets people have known about, and you can explain that too. But let's talk about what this technology is. This is a brand new system, and it's a really interesting way of using sound to actually create work, to actually build structure and strength. So if you could talk about that a little bit.
This has been a tremendous amount of fun and continues to be. Back in the 50s, NASA published a paper that if you take a tiny orifice or hole in a plane and you trap sound on one side of the orifice, well, those sound waves have to try and come through that hole, okay? But sound waves are just a motion of expansion and compression. They don't actually, nothing travels. The molecules don't end up on the other side of the room when you hear something. So what happens is the little molecules go in and out of the hole like an air piston, okay? That's a wonderful piston because it doesn't have to be lubricated. It can't wear out. But when it emerges, it hits the molecules in front of it like billiard balls and sends them streaming. And as they go forward, they pull in other molecules from the side that become part of the stream. So it makes a wonderful fan, and they have been used for cooling fans and jet streams. Very, very efficient, very tiny. But they weren't useful for closed systems, meaning you couldn't harvest this pressure here and trap it and blow up a balloon with it, and you couldn't harvest the vacuum or the lower pressures and deflate something with it. You couldn't do work with a Synjet that was in a closed system. You could just basically blow like a fan, okay? So what we did was we took this Synjet, synthetic jet hole, and we put a tube coming right in the plane into the hole. Now, as the pressure goes through the hole, Venturi tube-like, it causes a vacuum in this, and now you start to have your closed system, okay? Because it doesn't want to go back down the hole, and it's much easier for it to start to fill. And this became a very, very high-resolution pump that, because sound is so controllable, when you're panning your stereo, you can pan it from left to right, and if you leave it there, it'll stay right there forever. Well, this pump is very, very high resolution. It's very capable of pressures as low as capillary pressures in the brain.
Wow.
It can also do tremendous work given a sound source that is high enough.
And you can connect them in series to, basically you're creating a net gain in the molecules filling the space, and so you create a series array of these pumps, and you can actually do quite a bit of detail work. What
we discovered, this pump actually has 12 pumps in it. So this is very tiny, and it's only about 2.5 millimeters long and 4 millimeters wide, or 2.5 millimeters wide and 4 millimeters long. It has 12 in it, and they are in series, and as they are put in series, they sum their pressure. So whatever the pressure was of the first one then gets summed with the second, and then added the third and the fourth and the fifth. And we've gotten out of that little pump 2.5 pounds per square inch off of a hearing aid speaker. So it's tremendously efficient. It's tremendously high resolution. It has wonderful applications in biomedical, for drug pumps, for micro-robotics, and it runs off of a hearing aid battery, which is also very
convenient. We have a question in from Ned Smith of Business News Daily, and he's curious about, obviously, the commercial applications. When might we see the commercial applications, and are there ways the technology could be used besides in the hearing industry? And you just touched on a couple, so it's a nice lead into that.
Sure. Well, these ear tips should be on the market very soon. We're in negotiations right now with several companies. As you can imagine, any company that is able to simply add an ear tip to their product and have it be capable of being listened to at much lower volumes and therefore safer and sounding better is quite an attractive asset to. The inflatable bubbles, we're in negotiations with some of the professional audio manufacturers in Europe, and they've had this technology for a couple of years and are quite enthused over it. They said that being in the industry since the 40s, that they knew everything there was to know about speakers in the ear until they ran into this, and now it's a whole new field to discover. As far as that product will probably be available within a year and a half on the market.
Sure.
But the ear tips will be available within months. Now, the valves are very, very easy to manufacture.
This is the diaphonic pump?
This is the diaphonic pump. And we can cut 4,000 of these out of a 8.5 by 11 sheet. This is laminated material cut with lasers, so they're very, very easy to make and very, very reliable. So those are just waiting for applications from imbuing dyes into microscopic specimens under microscopes and lenses and that sort of thing. But their applications in linear actuators, pneumatic linear actuators, are tremendously precise, and it's a brand new device, so the field is open.
That's great. All right, so I'm going to go ahead and wind this down. One of the questions I wanted to ask before we close is, what are you going to do now? What's the next development step? What research still has to be done to make sure you're where you need to be?
Well, this is admittedly limited research. Everybody that we put these in ends up saying that it's louder at lower volumes, but this begs the study, formal studies. It begs studying how much these trapped volumes impinging on the tympanic membrane actually do contribute to states of health that we're trying to solve. We certainly don't know enough about this because we didn't, as I'm fond of saying, just happen upon a gadget. We happened upon a whole field of study.
Right.
And I'm sure there's lots to be discovered about this. We have various submissions for studies in right now, and all of this, including one of the neatest aspects of this is that audiologists have told me that they see lots of what are called leathered eardrums. And there was a study recently in Europe where gerbils were put in aquariums. You can find this online, or I'll put it on our website. And the gerbils were put under aquarium barometric pressure changes that amounted to the kind of pressures that I'm talking about on the eardrum, and within a matter of days or weeks they formed an extra layer of epithelial cells on their tympanic membranes, just like calluses, okay? And audiologists are telling me that they see lots of leathered eardrums from what they call misadjusted hearing aids that are battering the eardrum. And our hope is, and one of the basis of our new study, is to find that when these pressures are absorbed by these diaphonic lenses or these bubbles, that maybe those leathered conditions will go away, just like my calluses on my fingers go away when I don't play my guitar.
Right.
So
right.
Those are some of the things that are potential studies from this, as well as the Journal of American Medical Association recently published last year that there's a 70% chance or increased risk of hearing loss from the use of personal listening devices, and this was a cross-sectional study of children in Australia. Now, there's no reason for that. We have a solution, we believe, to that you can listen to these devices and not be at any risk, or at least be at a lesser risk, because listening at lower listening volumes is what's being recommended, and we have a way of doing it where the person no longer wants to turn it up louder because he can't really hear it or enjoy it.
Absolutely. It's great research. All right, thanks, Steve. And thank you for joining us. The webcast is being recorded. We'll have a version of this available in just a couple hours, along with some multimedia available on their website and on ours on the 13th. This is embargoed until the 13th. The papers will be presented on the 14th at the Audio Engineering Society in London. And that concludes the broadcast. Thanks very much.
Thank you.